Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about the basic definitions in electrical circuits. So first we will start with basic definitions of the electrical current. So what is meant by the current? So there are many definitions for the current, of course, but a simple definition here, as I mentioned, as you can see, current is the rate of charge of flow. So which means how much charge is flowing through a conductor in a second. That is called the current. And here the current or the units of the current is here amperes. So we measure the current in amperes. So 1 ampere is equal to 1 coulomb per second. So the amount of the energy passing through a conductor in one single second. So that is the ampere. So here ampere is equal to coulomb per second. Okay. And here we can also define the current is the rate of flow of electrons in a conductor. The rate of flow of electrons in a conductor is also called as a current. And here the current must be designated with both direction and the magnitude. So the current having both direction and magnitude. So here you can see there are two cases. First one and the second one. So in these two cases, let us consider the current flowing through this conductor is 3 amperes. So here this 3 is the magnitude of the current. Okay. And here the direction of the current, as you can see, let us consider this is A and this is B. And here this is A and this is B. So in the first case, the direction of the current is from A to B. So the direction having magnitude which is 3 amperes and the direction is from A to B. So here this arrow mark indicates the direction of the current, which means the direction of the current is whether it is from A to B or B to A. And in the second case, as you can see here, this current in the second case also is 3 amperes, which is 3 is the magnitude. Okay. So of course here the magnitude, either it may be positive or the negative, but I will also let you know what is mean by this negative sign in the magnitude and the positive sign in the magnitude. So which means here the direction of the current in this case is from B to A. It is indicating the direction is B to A. Okay. But actual direction of the current is A to B. Why? Because here the magnitude is representing with a negative sign. Okay, minus 3. So here the negative sign represents the opposite direction. I mean the current flow is the opposite direction with respect to the direction which is indicated here. Which means here the direction indicated, I mean according to this arrow mark, the direction indicated, I mean the current direction is from B to A. But here for the magnitude it is indicating as a minus 3. So minus 3 means the actual current is flowing the opposite direction to the indicated current, which means the actual current is flowing from again A to B only. Okay. So that's why here the current must be designated with both direction as well as the magnitude. So the direction is whether A to B, okay, or B to A. And the magnitude is how much of current is flowing, okay, from A to B or B to A. That is the magnitude. So this is about the basic definition of the current. Okay. So which means here in both cases current is same, which is 3 amperes. Okay. And how then the current is represents? Here either it may be the capital I or it may be the small I. Here I am not going to discuss about whether it is a DC or AC, just a current in both cases, right? So the current can be represented by either I or small I or the capital I, right? Then here, as you can see, according to the basic definition, the rate of change of electrons through a conductor, or the rate of what is that here, or the rate of charge flow is also called as a current. Okay, so here, that's why here it can be also expressed, the charge means here the Q, okay, and here the time means T. Okay, so here I is equal to Q by T, or here the rate of change of charge, okay, which means here we can also represent the current I is equal to dq by dt. Okay, in both cases, the current units or the current is measured in terms of amperes, that is coulomb per second, because the unit for the charge is coulomb and the unit for the the time is second, so the coulomb per second is nothing but ampere. Then coming to the voltage, the basic definition of the voltage. Here, as I mentioned, the capacity of the charged body to do work is called its electric potential. So, in another terms, the voltage is also called as the potential difference between the 2 points. The voltage across the 2 points or the potential difference between the 2 points. Voltage or the potential difference, both are representing the same. Okay, so here the potential difference or the voltage is nothing but the capacity of the charged body to do work is called its electric potential. Then what is actually voltage and how the voltage is measured? Okay, and what are the units of the voltage? So which means when 1 joule of work, because here according to definition, a charged body to do work, okay, so the work is 1 joule of work is required to move 1 coulomb of charge from A to B, then there is a voltage of 1 volt between A and B, which means the potential between the electric potential between the A and B is 1 volts. Okay, so the work is 1 joule, okay, and the charged body, okay, because when the work is done, it moves from one point to another point. Okay, if there is a displacement, then which means the work is done. Okay, so that's why here the voltage or the 1 volt is nothing but when 1 joule of work is required to move 1 coulomb of charge from point A to B, then there is a voltage of 1 volt between the points A and B. And unlike the current, here the voltage, of course, this the voltage is represented by V, capital V or the small v, and the voltage across an element or the potential difference between the 2 points is required both magnitude and the polarity. So here the in case of current, magnitude and direction, but in case of voltage, it is having the magnitude and as well as the polarities. Polarities means like plus and minus. So because this is in between the points A and B, right? Point A and point B. So whether the point A is polarity is positive with respect to B or negative with respect to B, which means suppose let us consider point A is positive, then the point B is negative. Or maybe if the point A is negative, then the point B is positive. So the voltage having both polarities as well as the magnitude. So here let us take 2 examples in figure A and figure B. So in figure A, here the potential between or the voltage across the point A and point B is, let us consider, here we are representing the voltage as in small v, equal to minus 5 volts. Okay. So here the point A is positive with respect to point B. Okay. So then here let us consider VAB equal to minus 5 volts. But here as you can see, VAB is equal to plus 5 volts. Okay. But as you can see, the polarities A and B, here the point A is positive with respect to B, but here the point A is negative with respect to B. Okay. So which means let us consider here, if the voltage across the point A is, this is minus 5 means, if you want to change the polarities, okay, I mean A is positive and B is negative, then you must represent VAB is equal to minus 5. So which means either you have to change the polarities, I mean of A and B, or you have to change the sign of the magnitude. So which means here, I mean practically this, in the first case, okay, voltage, let us consider here VA and this is VB, then VA is equal to VB. Both magnitude and polarities are same. And coming to the next example. Okay, so here it is a reverse case, right? So here plus and minus. So V is equal to 5 volts. So let us consider here VC is equal to plus 5 volts. Okay, and here VC it is representing as a minus 5 volts. But as you can see again here, in case of C, the polarities, I mean A is positive with respect to B, but here A is negative with respect to B, which means let us consider this is VAB. Okay, positive and negative. VAB is equal to 5 volts, and here the positive is B and negative is A. So let us consider here VBA is equal to minus 5 volts. So here VAB is equal to 5, VBA is equal to minus 5 volts. Let us consider here this is again VAB is equal to 5 volts. If you want to change the polarities of A and B, then the minus sign of the magnitude is also changed. Then this is also, we can write VAB is equal to, okay, here I am changing the polarities. So A is positive with respect to B. Then here you have to change the sign also. So here minus of minus 5 volts. Okay. So which means VAB is equal to again 5 volts. So here VAB is equal to 5 volts and here VAB is equal to 5 volts. So which means here again this VC is equal to VB. The same way here also the VA is equal to VB. So here the voltage across the voltage across an elements require both magnitude as well as the polarity. Okay. So here this plus and minus are the polarity of the magnitude, or the polarity of the the voltage across the terminals will depends on the terminal, the polarities of the terminals. Okay. So if A is positive with respect to B, if we consider V is equal to plus 5 volts, okay, if polarities are interchanged, then V should be minus 5 volts. Okay. And because again here actually V is equal to minus 5 volts, again I have changed the polarities, then minus of minus plus, then V is equal to 5 volts. Okay. So this is about the basic properties of the voltage across any two terminals, or the voltage across an element. And here as you can see, there are two statements. If the voltage is from plus to minus, which is nothing but fall in voltage. So high potential to low potential. Of course here positive high potential to low potential. So the potential difference between these 2 points is nothing but the voltage. Okay. So plus to minus is fall in voltage. So high potential to low potential, it is fall in voltage, we usually call. And if it is minus to plus, then the rise in voltage, which means from low potential to high potential. Okay, right. Then, of course, as I told you, there are so many definitions here. Here, another definition for the voltage is the potential difference between force applied to two opposite charged particles to bring them as near as possible is called, as potential difference. Okay. So which means here V is equal to W by Q. Okay. So which is represented by volts. Of course, there are steady state voltage and time varying voltage. In the steady state, we usually W by Q, and in the time varying dW by dQ, which means here the dW will change with respect to the time. Okay, dW by dQ. Okay, in both cases, this is the voltage is measured in terms of volts. And then when coming to the basic definition of the power, as we simply know, P is equal to V into I, the voltage into current is nothing but the power. Okay, so which means the rate at which work is done in an electrical circuit is called its electric power. The rate at which work is done. So electric power equal to work done in the electrical circuit per time. Okay, so that is watt per time, because here work done. Okay, that is called, that we usually represented as a V into I. Okay, and the units for the power is watts. The unit for the power is watts. We usually represent as a W. Okay, for the current is ampere, and for the voltage is volts, and for the power is watt. We usually represent the power as a the capital P or the small p. So the power required to push a current I into the voltage, which means coulomb per second, okay, into joule per second. Joule per coulomb. Okay, because here this is work by charge. Okay, is P is equal to V into I. Okay, that is measured in terms of watts. Okay, same like this power, okay, is having both magnitude as well as the polarity, whether it is a positive power or the negative power, like the positive voltage or the negative voltage. Okay, so when power is positive is nothing but the element is absorbing the energy. Okay, when power is positive, the elements is absorbing the energy, which means here the source the source is supplying the power, because when the source is supplying, okay, then only the elements will absorb the energy. And when power is negative is nothing but the element is supplying the energy, which means here the source is taking the energy. Okay, that is represented by the negative. That we will understand clearly when we are going to solve electrical circuits. Okay, but this time just remember what is mean by the positive power and what is mean by the negative power. Okay, so here you may get out element means what is an element. Okay, so let us consider the basic electrical elements. Okay, that also we will see what are the various types of electrical elements. Element is nothing but, let us consider at this particular point, resistor. Okay, so when power is positive, the element is absorbing energy, means the resistor is absorbing the energy. Okay, of course in this case we should not consider here element as a resistor, because the resistor should not supply the energy. Okay, so there is another element. Let us consider the element is either the inductor or the capacitor. Okay, so because at this particular point we don't know what is the purpose of the resistor or inductor and capacitor, so that's why it is very difficult to understand why in this case we are considering as a resistor and why in this case we are considering as an inductor or capacitor, or in both cases we simply can consider capacitor or the inductor, right? So here some basic examples that I have mentioned here. So in the first case, okay, so we have to calculate what is the power in first case A, case B and case C. Okay, there are three different elements. So let us consider here the power. Okay, of course here the current is in this direction, because the current having both magnitude and the direction, and the voltage having the magnitude and the polarities. Of course you may get doubt here, this current also having some polarity, which means -3, but in the current case the polarity represents the polarity, which means especially the negative polarity represents, okay, the actual current flow is opposite to the current which is the current direction which is represented, because here the current direction which here it is representing like this in this direction. So minus 3 means the actual current flow is this direction. Okay, so that is mean by this polarity in case of current. Okay, don't get confused. Then here, as we know, P is equal to V into I. So in this case, the voltage is 2 and the current is 3. Then 6 watts. The power is 6 watts. In the second case, P is equal, okay, voltage is minus 2 volts. Then minus 2 into the current is also minus 3 amperes. So minus 3. So minus into minus plus, then 6 watts again here also. And here P is equal to, here voltage is 4 and the current is minus 5. Then here it is minus 20 watts. So which means the plus, the polarity of the power, okay, whether it is a positive power or negative power. So positive power means here it is the element is absorbing the energy, and the negative power means the element is supplying the energy. That is the difference between the positive and negative power. Okay. So here, of course, here they have already mentioned. So in the PA it is plus 6 watts. Okay. And in PB here it is also plus 6 watts. Okay. But in PC here it is minus 20 watts. Okay. So the power having both polarity and as well as the magnitude. Polarity, magnitude. Polarity, magnitude. This is about the basic definition of the power. So, of course, here again, the rate at which the electrical energy is converted into another form of energy, okay, are equal, or we can also call as power is equal to the product of current and voltage drop. Okay, so P is equal to what is that? Work done in a time, that is the rate of what is that electrical energy. Okay, here energy is nothing but we are representing as a watt. Okay, W work by T time, which is equal V into I. Okay, so we usually present as a watts, because W is equal to work done per time is nothing but the power. Then coming to a basic electrical law, which is the Ohm's law. Okay, Ohm's law at constant temperature. So what the Ohm's law is defines, the Ohm's law states that at constant temperature, this is very, very important, at constant temperature, in an electrical circuit, the current flowing through a conductor is directly proportional to the potential difference we applied, which means let us consider an element resistor A and B. So let us consider the potential difference between these A and B is VAB, let us consider, okay, or just simply V. And the current flowing through the conductor is, let us consider, I. And the resistance of this resistor is, let us consider, R. Okay. So according to this Ohm's law, the current flowing through this conductor or an element is directly proportional to the voltage across this element or the potential difference across the element. So which is nothing but the I is directly proportional to V, or in another terms we can also call it as V is directly proportional to I. So if you eliminate this proportionality, then we will get a constant which is called R, that is the resistance of a resistor. Of course, the resistance of a particular resistor is constant. Okay. So then Ohm's law we can simply state as a I is directly proportional to V. So the current flowing through the conductor or the current flowing through an element is directly proportional to the voltage across an element. Okay. In other words, I is equal to V into R. This is the Ohm's law. Okay. So don't forget, this is at constant temperature. Okay. This Ohm's law is at constant temperature. Without mentioning the constant temperature, This is wrong. The statement will be wrong. Okay, so which means I will not directly proportional to V. When only at constant temperature I is directly proportional to V, which states the Ohm's law. Okay. So then the limitations of the Ohm's law is, of course, these Ohm's law is applicable only for the conductors. Of course, what is that? Only for the metallic conductors such as copper, silver, etc. You know what is mean by conductor and insulator? Okay. So conductor means it will allow a free flow of electrons, which is nothing but the conductor. An insulator means which does not allow the flow of electrons is the insulator. Okay. So this Ohm's law is applicable for only metallic conductors such as copper and silver. And it is not applicable for the electrical circuits such as semiconductor devices, transistors, etc. Okay. So we will discuss again later what are the semiconductor devices. Okay, like all transistor, IGBT, MOSFET, these all are the semiconductor devices, right? And diode is also a semiconductor device. So which means if you represent graphically Ohm's law, because when I increases, proportionality means, okay, when if you are increasing I, then voltage is also increased with the same proportionality. So that's why you will get a linear curve. So here, if you are increasing V, then I will also increase proportionally. So that's why, which means if you join these points, then you will get a linear curve. This is, which means it is following the Ohm's law. Okay, so that is called, those type of conductors are called the ohmic conductors. Okay, so those conductors which obey the Ohm's law are the ohmic conductors. Okay, and these are the non-ohmic conductors like such as semiconductor devices, because here the voltage is not directly proportional to current. Okay, so which means it is a non-linear curve. So that's why it is a non-ohmic conductors. Then here a simple circuit, because till now we have discussed what is mean by power. P is equal to V into I. Okay, and from the Ohm's law, V is equal to I into R. Okay, so from this we can also write I is equal to V by R. Okay, and R is equal to V by I. Like that we can define many equations. Okay, so from this, as you can see here, first V. Okay, so here V is equal to I into R. That is the basic equation that we can get from the Ohm's law. V is equal to I into R. Okay, suppose if you want to define V in terms of P, okay, V is equal to P into I also we can write, because what is mean by P is equal, what is mean by P? P is equal to, okay, sorry, not P into I, P by I. P by I. Okay, so here V is equal to, what is P? V into I by I, then I gets cancelled, then V is equal to V. So we can also define in terms of power, that is V is equal to P by R. Okay, and also we can define V is equal to square root of P into R. Why? Because here V is equal to, what is mean by P? Okay, P is equal to V into I. Okay, P is equal to V into I into R. Okay, I means I is equal to V by R. Okay, so V is equal to square root of V into V by R into R. So R gets cancelled, then V is equal to square root of V square. This gets cancelled, then V is equal to V. So here V can be defined in terms of current and resistor, V is equal to IR, and in terms of power, V is equal to P by I, and in terms of power and resistors, V is equal to square root of P into R. Similarly, the current also. Okay, so this we can call as a, just for our simple understanding. Okay, So we have drawn this circle. Okay. So even I is equal to also, because as we know V is equal to I into R means I is equal to V by R. This is V by R. And similarly I is equal to, we can also write P by V. And I is equal to square root of P by R. Okay, as you can see here, these are almost similar, because here into is there and instead of into here it is divided by R. Here just I replaced by R. Similarly, you can define R also. R is equal to, become from here R is equal to V by I. So R is equal to V by I, and R also can be defined V square by P, and R also can be defined P by I square. Similarly, P also V into I or I square R or V by R, because here P is equal to V into I from the same. Okay. So here V is equal to V is equal to I into R into I. So then I into I square into R, P is equal to. From here, from this formula, we can define this formula. And from this, we can define this one, because I is equal to V by R. Okay. So I is equal to V square by R square, because here I square is there. Instead of I have substituted V by R into R. So R gets cancelled, then P is equal to V square by R. Okay. So like this, by using this circle, okay, you can define, or you can define the voltage in terms of any other, other three, parameters like current and power and resistor. And here current also another three variables. So like this, we can define the equations by using this, by applying this Ohm's law. Next, then when coming to the electrical elements, okay. So first we will classify and what are the various classifications of these electrical elements. Okay. Then we will discuss one by one. Then these network elements are classified into various types. One is active element, passive element. Okay. Then linear and non-linear elements. Then unilateral and bilateral elements. And then time variant and time invariant elements. And then lamp or distributed elements. Okay. So then total network elements are classified into 1, 2, 3, 4, 5, 6 various types. Of course, not only 6, because here linear element is there and again non-linear. Again, this is classified into 2. And here unilateral and bilateral. Same time variant and time invariant, and lamp and distributed. And again, these elements are sub-classified. Okay. Here the active elements are classified into two different types. One is independent source and dependent source. And again here, the passive elements also, okay, and what are the different types of passive elements are resistors, inductors and the capacitors. And we will see what are the active elements also. Okay, usually the voltage source and the current source are the active elements, and again the voltage and current source are classified into independent sources and dependent sources, that we will discuss. Okay. Then here the independent sources are again ideal and the practical. Again the independent sources sub-classified into ideal and the practical sources. Okay. And again the practical, in case of ideal and practical sources, as I told you, which means ideal voltage source is there, ideal current source is there. Similarly, practical voltage source is there, practical current source is there. Okay. So one by one we will discuss what is mean by ideal voltage source and what is practical voltage source, and similarly what is ideal current source and what is ideal practical current source. Okay. And similarly in dependent sources also, okay, voltage dependent voltage source and current dependent voltage source. Similarly, voltage dependent current source and current dependent current source, which means again dependent sources are classified into four different types. Okay. So what are the linear elements and non-linear and unilateral, bilateral, that we will discuss in next coming classes. Then coming to the active elements. Okay. So active elements are the source of energy, are the elements which can deliver the energy are called the active elements. Okay. So usually in an electrical circuit, okay, the basic elements are active and the passive, which means voltage source or current source or resistor or inductor. Let me draw here one simple electrical circuit. Okay. So this is a simple electrical circuit. So let us consider R1, R2 and V. So here this is voltage source is one element and resistor are the another elements. So here these voltage source will provide or the source of energy, or these voltage source deliver the energy to the the other elements. Okay, here the resistor is the energy absorbing elements. Okay, so the elements are the source of energy. Okay, the elements are the source of energy, or the elements which can deliver the energy is called the active elements. So the best example for the active elements are voltage sources and the current sources. And then of course, again, as we know, the voltage and current sources, AC source and DC source, okay, that we will discuss in detail later. Okay, so again, these active elements are classified into independent source and dependent source. Okay, independent source and dependent source. So here the names itself, as you can see, first let us go with the independent source. So active elements includes independent voltage source and as well as the independent current source, because the active elements are voltage source and current source. And again in the active elements, the classification is independent source and dependent source. So when coming to the independent source, which means independent voltage source is there and independent current source also there. Okay, so the independent voltage source maintains, okay, fixed, okay, which is not affected by any other quantity in a circuit. Okay, which means the value of the voltage source will not depends on, okay, the value of the voltage source will not depends on any other element present in the circuit, which is called the independent source, which means it is independently, the value of the source will not depends on any other element which is present in the circuit. So the name itself, it is giving the definition independent source. So it is independent, or the value of the source is either it may be voltage or current is independent. Okay, so which means the value of the source, the voltage or current source will not depends on any other element in the circuit. Similarly, the some current source is also maintains a current, okay, which is the fixed value, which is unaffected by any other quantity in the circuit. That is mean by the independent source. Okay, so again there are two different independent sources are there. One is ideal energy source and another one is the practical independent energy source. So then now we should know the difference between ideal and the practical. So here also the name itself, it is giving the definition, ideal and the practical. Okay, so ideal means by neglecting some properties of that particular thing. Okay, so in case of ideal, again ideal voltage source is there and ideal current source is there. Similarly, the practical voltage source is there and practical current source is there. So we will discuss one by one what is ideal voltage source and what is ideal current source, and what is practical voltage source and what is the practical current source. Okay, so here first let us consider ideal voltage source. Okay, so the ideal source are those imaginary electrical sources which provide constant voltage or the current to the circuit irrespective of the load currents. So which means, actually, before going to know about the ideal source, okay, it's better to know about the practical source, because every source, okay, having some internal resistance. Practically every source having some internal resistance. If it is a voltage source, then the internal resistance is connected in series with the particular voltage source, and if it is a current source, the internal resistance is in parallel with the current source. That is in practical. Okay, but in ideal case we will neglect the internal resistance of the source. Okay, so that is mean by the ideal source. Okay, so by neglecting the internal resistance of the particular voltage or current source, then the value of the voltage of the particular source or the value of the current of that particular current source is constant. So which means it will not depends on the value of the the current flowing through the internal resistance or the voltage across the internal resistance, which is connected to the voltage or the current source. Okay, so that's why here you can see in ideal source it don't have any internal resistance, but it is impossible to build a source with zero internal resistance, because practically every source having its some internal resistance. So that's why that is the practical source, which means practically every source having some internal resistance, right? So which means here you can see this is the ideal voltage source. Okay, so which means this is only the voltage source. It doesn't have any resistance which is connected in series with this. So that's why this representation is called the ideal voltage source, and that's why here the voltage across the terminals A and B is always constant with respect to the time. Okay, and then when coming to the current source also, here there is no internal resistance connected across this current source. So that's why here the current flowing through this element IAB is also always constant with respect to the time. But whereas in practical voltage source, okay, so in case of voltage source, the internal resistance is connected in series with the voltage source. Then the voltage across these two terminals AB, okay, the voltage across these two terminals AB will depends on the current flowing through the resistor, because as we know here VAB, okay, so VAB is equal to the voltage here V minus the voltage across the resistor VR. Okay, so V minus here the voltage across the resistor will depends on the current flowing through this resistor. So I into R. Anyway here R is constant, so the variable is I. So which means this is VAB. So the voltage across the two terminals VAB is depends on the current flowing through the resistor, the amount of the current flowing through the resistor. So here if you increase the current value, then here the VAB is decreased. So that's why here, okay, this is the practical source. That's why the voltage across the VAB is not constant. It is depends on the current flowing through the internal resistor. Okay, so this is the practical voltage source. And when coming to the practical current source, here the internal resistance in case of current source, the internal resistor is in parallel with the current source. Okay, then in this case the current flowing through this current flowing or the current supplying by this current source will depends on the voltage across the terminals, the voltage across this resistor. Okay, so that's why here as you can see when time is increasing, okay, the current supplying by this current source is not constant. Okay, so this is the difference between the ideal and the practical. So one simple understanding, the ideal voltage source, it doesn't have any internal resistance. Okay, but in case of practical source, the practical source having its internal resistance. Okay, so that's why the value of the practical source will depends on the internal resistance, either the voltage across the internal resistance or the current flowing through the internal resistance. This is about the difference between the ideal and the practical sources. Okay, either it is ideal voltage source and ideal current source, and as well as the practical voltage source and the practical current source. Then coming to the independent and dependent sources. Okay, so in case of dependent source, okay, again it is classified into 4 different types. One is voltage controlled voltage source, or the dependent source is also called as a the controlled source. Okay, so which means voltage controlled voltage source, which means the voltage source is controlled by the voltage, and the voltage controlled current source, which means the current source is controlled by the voltage source, and the current controlled voltage source, which means the voltage source is controlled by the current controller, or the current, and the current controlled current source, which means the current source is controlled by the current controller. Again another current. Okay, so it is categorized into these four various types. Okay, so here you can see the active elements includes dependent voltage source and dependent current source, and these sources whose output voltage or current is not fixed. Okay, because in case of independent, it is fixed because it will not depends, or the value of the voltage source or the current source will not depends on any other element. But in case of dependent, okay, so the value of the voltage or current source will depends on the other element present in the circuit. Okay, which means let me give some simple example. So here one resistor is there, here also one resistor is there, let us consider, and here one more resistor, and here some current source is there, let us consider. Okay, and here let us consider R1, R2 and R3. Okay, here it is V. Okay, and here it is I. If V is equal to, let us consider 3 into I, let us consider. Okay, so here the voltage or this is the voltage source. So the value of the voltage source V is depends on the value of the current source which is connected in the same circuit. Okay, so here V is equal to 3 into I, which means let us consider, suppose if I is equal to 2 amperes, then here V is equal to 3 into 2, 6 volts, and if I is equal to 3 amperes, then here V is equal to 3 into 3, 9 volts. So which means the value of these voltage source is depends on the value of the current source which is present in the same circuit, which means here you can see the output voltage or current is not fixed but depends on the voltage or current in another part of the circuit. Okay, so which means here the voltage of this source is depends on the current source which is connected to another part of the circuit. Okay, so then what kind of the dependent source it is? Because here these voltages depends on the current. Okay, which means this voltage is controlled by the value of the current which is connected in another part of the circuit. So that's why it is a current controlled voltage source. Okay, so the current controlled voltage source. So this is the current controlled voltage source. Similarly, let us consider here, instead of here the current source. Okay, so let me put again one more voltage source. Let us consider here it is some V1. Okay, then V is equal to, again let us consider 3V1. Then the value of this voltage source is depends on the value of this voltage source, another voltage source connected in the another part of the circuit. Okay, so which means here it is this voltage source is controlled by the another voltage source. So that's why it is voltage controlled voltage source. Voltage controlled voltage source, because here the controller is voltage. So like that, the value of the voltage source or the value of the source is depends on the value of another element which is connected in the same circuit. That is called the dependent source. Right. So here, as we can see here, so here VAB is equal to K into VDC. Okay, so that's why, which means this is voltage dependent voltage source. Okay, and another one here, this IAB is equal to N into VCD. So which means here the value of IAB is depends on the value of VCD. So which means here the value of VAB is controlled by the value of the VCD. So voltage controlled current source. And similarly here, this is current controlled voltage source, and here it is the current controlled current source. As you can see, this is voltage controlled voltage source because this voltage is controlled by the another voltage which is present in the same circuit, and here this is voltage controlled current source. Okay, because here the current source is controlled by the voltage source which is connected in same circuit, and this is current controlled voltage source. Okay, because this voltage source is controlled by this current source, so that's why current controlled voltage source. And here it is current controlled current source because here it is current controlled current source. Okay, so I hope everybody is clear about the dependent sources. Okay, so voltage controlled voltage source, voltage controlled current source, and current controlled voltage source and current controlled current source. So these are the various types of the dependent sources. Okay, so now you understood what is mean by voltage controlled voltage source. What is mean by independent source and the dependent source. Okay, thank you. In next class we will discuss the remaining topics.
Like, share and subscribe. Hit the bell icon for more updates.